Hello, everybody. Thank you for joining us. I'm Milene Guiar from Toronto International. I'll be hosting this webinar today. Bradley, thank you for joining us. Please introduce yourself and start whenever you want the presentation.
Excellent. Thanks, Milene, and everyone else with the Water Loss Specialist Group for hosting this webinar series and for inviting us to present today. Slide, there we go. So my name is Bradley Jenks, and I'm with Hydrotech and Associates, a consulting firm based in Toronto, Ontario, specializing in the hydraulics of urban water systems. So today we will be presenting on a water loss management testing program across the province of Ontario, where we're deploying a mobile unit or a cost-effective diagnostic tool to collect field data and support and inform water loss investment decision-making. So I'm joined with Fabian Papa in this conference room. Fabian is the project lead and has extensive experience consulting here in the Toronto area. You may also recognize him from various different international conference presentations on a bunch of different matters. I'm also a graduate student at the University of Toronto. My thesis supervisor is Professor Brian Carney. Brian is world-renowned in the field of water system hydraulics, energy investigations, and many, many other things. So a brief introduction to Hydrotech. Brian co-founded the company back in the late 1980s. Where the core focus was looking at hydraulic transient modeling, which made the bulk of Professor Carney's research. And since that time, the company has gone on to develop many different business lines, one of which is linked to this presentation, is pump performance and energy efficiency testing, with the same objective of reducing inefficiencies in our water systems to reduce wasteful energy consumption. And we'll tie in a little more on that in a few slides. So in order for effective water loss management decision-making, the presentation will walk through the following topics. The first beginning with understanding and evaluating the uncertainty associated with some of our initial efforts in terms of leakage and system performance. From there, as I mentioned, the project looks at developing and deploying a mobile unit to collect data cost effectively. And then looking at that data, how do we objectively assess it to see how our system is performing, being the last section. And then we'll go into a case study from one of the testing sites in the program and look at it in more closer detail. So to begin, the graphic on your left is from the Environmental Commissioner of Ontario report in 2017, which looked at inefficiencies in our water systems and as they relate to energy consumption, and one of the notable ones being leakage. So a survey was conducted where between 10 to 20% was quite typical of system leakage in utilities across the province. And as we know, not only is that a waste of water as a resource, but also of energy and financial resources therein. Now, the economic incentives, or in other words, the marginal cost to produce the water, does vary from municipality to municipality, from those who source their own water and to those who purchase at wholesale, at bulk, from other utilities that are connected. And so the case study that we're going to look at later in the presentation is from one of those municipalities who pays quite a high price relative to others for that water, and hence the impacts are much greater. And then there's the potential for damage to other systems adjacent to the water distribution network, whether that's damage through corrosion, electrical faults, or decreasing capacity for our surrounding sewer networks. And so focusing on the energy component being the primary driver for this project, as water leaks, so does energy, as the Environmental Commissioner report noted. If we look at the pumping power relationship, and we look at the different components, we have the unit weight of water, which is a constant. We have the pump efficiency, which, as I mentioned, is started as a project similar to this with Hydrotech, and their partnership with the primary funding agency of the Ontario Power Authority that looked at pumps across Ontario and how they were performing, and again, having a direct impact to the energy consumption in our systems. And then this project, looking at total system demand being directly proportional to the amount of energy required, and leakage being a component therein. As well as if we look at the total lift that we need to overcome in our systems, note too that as we increase the demand, so as leakage exists in the system, the dynamic losses also increase. And so we need to overcome that energy as well. And as I mentioned, the independent electricity system operator is the primary funding agency of this project, as they essentially the power industry in Ontario, as they realize that any inefficiencies in our water systems are also an inefficiency upstream into their system. And so their funding here is essentially demand side management. If they can reduce energy consumption, municipalities being a large consumer in their power network. So looking at a conceptual image of energy consumption in our water systems, we can see we need to overcome the total lift, static being the elevation and any pressure that we're providing to consumers, as well as those dynamic losses from hydraulic and frictional characteristics. And so as we increase the demand through leakage or actual consumption, we're increasing the amount of energy that we need to input into the system. And so there are also environmental impacts further upstream to the energy component. Now, conventional approaches to looking at water loss management, as I'm sure many of you in the audience today know. First, we can look at an initial top-down assessment, otherwise known as a water balance or water audit, which is essentially an inventory of system inputs and outputs. And this is a desktop study with modest effort required. On the contrary, if we look up from a bottom-up analysis, more at the pipe level granularity, or in one case, the use of district metered areas at a subsystem scale to monitor inflows across different areas of the network. And then we can get even more granularity in the data collection process using different detection technologies. Leaks make noise, and so we can listen to that noise and correlate where leakage may occur. And as the field testing methodology requires more extensive data, so too does the analysis effort. And so ideally, we want convergence between these two approaches to support and allow for confidence in the investment decision-making process. Looking at the water balance briefly, the top-down approach, I'm sure many of you, again, are familiar with the water audit structure and the process. And here we're looking for an estimate of real losses. And so if we look at all the inputs to this model, we've color-coded them with respect to an estimate of uncertainty that surrounds those input parameters. Like any model, inputs do have variability in them. In green here, we have the metered consumption, which typically have many devices in the build consumer devices in the process. And so any uncertainty that surrounds each individual device is going to be lessened as more devices are entered into the system. And so this is the statistical principle of the law of large numbers. On the contrary, when we have meter devices that are quite few and the ones in orange have the bulk of the flow going through the system, any uncertainty with those may have a larger impact. And then the different estimated components and the uncertainty that surround these depend on the procedures and data collection processes that are in place in the specific utility. And everything in the black text is a calculated value, which has a propagation of all these different uncertainties combined within. And so if we look at quantifying or evaluating the level of uncertainty, particularly pertaining to the estimate of real losses, as I mentioned, we have that propagation of uncertainty, which does generate a wide range of different outputs or decision-making outcomes when we look at that specific indicator. Different quantification methodologies The first being the most typical and simplistically used, the root sum of squares, are often referred to as the summation and quadrature. And so essentially, what's required for this method is just an expected value of each input component, as well as some measure of variability, whether that's a 95% confidence level or some uncertainty measurement. And the assumption with this approach, the core to the approach is the central limit theorem, which states that regardless of the input distribution of all the different input components, that output, that estimate of real losses will be characterized by a normal distribution. Another way to quantify the uncertainty is using Monte Carlo simulations, which is a probabilistic model. And in addition to the expected value of each component and some level of uncertainty, the model requires an input probability distribution, normal or otherwise, to characterize the variability of each component. And so if we look more closely at how the Monte Carlo simulation method works, we have our input distributions and their different levels of uncertainty and expected values on the left. As we go into the calculation process itself, the Monte Carlo simulation takes at random one value from each input component from those corresponding distributions, calculates the estimate of real loss over n trials. And so it does this over n times to statistically converge to the output distribution we see on the right. And so we can calculate different metrics to get a sense of the variability in what the estimate may be. So a quick example, using water audit data from an anonymized municipality here in Ontario. What's important here is looking at the confidence levels that are applied, as well as different probability density functions or probability distributions. Note that these are assigned and they're arbitrarily assigned to convey the concepts of the method. So we look at results, we can see here the output distribution. So not only we have our mean value, but we can also look at the histogram in terms of other metrics, the different percentiles that give us a coverage interval depending on what percentiles we're looking at. In this case, the 95% confidence level. And so this visually tells us that there is a range in the outcomes that we may have for the given inputs and their associated uncertainties. So it's important to realize that this is a range of values. On the right is just simply looking at the two methods, the root sum of squares and the Monte Carlo approach, and how the output distribution may not always represent a normal distribution. And so this plot is intended to show the deviation between the two. So the implication of this is that the Monte Carlo simulation approach is a robust method to quantify the uncertainty. So briefly, in summary, realizing that singular results of that top-down water balance may lead to poor investment decisions, and then the uncertainty that's associated with those input values do produce a range of possible different outcomes. And so understanding this is key to evaluating how our systems are performing in terms of this initial top-down assessment. Logically, the next step is to look at bottom-up approaches through the collection of data and reducing uncertainty in those areas that we are testing and collecting field data in. So if we look at typical bottom-up data collection methods, here they're presented in terms of the leakage assessment scale. And so on the far right, we have remote sensing, which harnesses satellite imagery to get a sense of what's going on in terms of leakage. However, being at such a large scale, the accuracy may be limited. On the contrary, we have pipe level, quite granular leakage detection techniques, one of them being acoustic listening. Elaine Lalonde gave a great presentation a few weeks ago on these procedures. And then we have district metered areas, which is looking at our system on a subscale in different areas and monitoring performance in those different components. And that's the focus of this Ontario-wide testing program that we're presenting today. So looking more closely at district metered areas, the division of water distribution networks into discrete sectorized areas, whether through natural boundaries or closed valves to isolate those areas. And so this conceptual diagram we have here is showing single inlet DMAs, although they could be dual inlet. The point is that everything that flow is captured into the system is measured and recorded. And so we can look at different flow profiles as a result, different statistics, trend analysis over time, how the system is performing. And then specifically relating to this project, looking at minimum night flow as an indicator of leakage. And so notable Canadian experiences are Halifax Water, as well as the City of Ottawa. Interestingly, a common influence between these two utilities is a longstanding IWA member, Ken Brothers. So looking closely at the minimum night flow methodology, we can see that a typical diurnal demand profile for our water systems. And in between midnight and 6 a.m., we have that lowest value in flow, which is when consumption, actual consumption, is at its minimum. And so any flow at this time, leakage constitutes the highest fraction of, and so we can use this as an indicator of how our systems are performing in terms of system leakage. A great graphic on the right provided by the City of Ottawa looks at one of their closed zones, minimum night flow plotted from January of 2019 each day for about 4 months. And we can see here that when new leaks are suspected to occur, that minimum night flow value jumps up. And then when they fix and locate and fix a leak, they can see that verification and reduction in flow through the minimum night flow analysis. And so near real-time assessment of how that zone is performing. So if we look at residential diurnal demands against non-residential diurnal demands here, we can see in predominantly residential areas, there's that consistent low flow overnight pattern that's repeatable across many different measurements presented here. However, if we look at the non-residential demand profile, there's quite a wide variability in that overnight demand pattern. And so for using that value, that minimum night flow value, in terms as a comparison across different areas, the implication of this is that it's best to focus in predominantly residential areas so we can compare system performance accordingly. Furthermore, if we look at summer irrigation, again, the principle of minimum night flow is that the actual consumption is at its lowest during that overnight period. And so when we do have irrigation or actual consumption in the system, we can't use this data reliably as an indicator of leakage. And so you can see here in an example that during the nighttime when there is irrigation, that flow values increase, and if not dwarf what otherwise would be a daytime demand. And so the implication of this is to focus minimum night flow measurements during months with no irrigation. If we look at implementation barriers to DMAs here in the Ontario context, as it relates to affordability, temporary solutions being insertion or clamp-on type metering technologies. And so these are periodic measurement techniques, which can be quite affordable. However, if we compare that to permanent installations, so here requiring a metering chamber, an inline flow meter with and without pressure management as an option, these costs do increase quite dramatically. Do note that these values reflect experiences in the Toronto market and might not be representative elsewhere in the world. And so with these values in mind, the logical progression is to use a temporary metering approach to collect data and allow for that evidence to support further decision-making if warranted. However, when we look at temporary DMA monitoring, there are limitations with these metering technologies, specifically as they relate to the low flow or low velocities in our systems. Our systems here in North America are designed for excessive fire flow requirements, resulting in quite large pipes. And as the flow, especially during the overnight period, gets quite low, so too does the velocity. And there's a limitation in terms of the data quality. So there's a trade-off here between cost and reliable data to make decisions from. So if we look more closely at these metering limitations, this graph, the first two plots in blue are intended to show a sample distribution of minimum night flow estimates across a number of different DMA sites in a client water system. And so the minimum night flow single inlet, we can see here that the MNF estimate across 50% of these sites is less than 3, see my mouse, 3 liters per second. And then the dotted line is just that minimum night flow divided by 2, looking at a dual inlet system, assuming the hydraulics are stable across that inlet. Now, if we look at the low flow detection limits for inline flow meters, which are characteristic of permanent installations, the best way to view this is anything to the right, flows are reliably able to be captured. So they can capture in the entirety the distribution of different DMAs across this utility. However, in green, if we look at the temporary metering technologies, both insertion and clamp-on, over different ranges of flow, especially using the clamp-on ultrasonic, we may not be able to reliably collect data. So the implication of this, again, is that if we want to collect data reliably, we want to look at inline flow metering technologies. However, these require conventionally permanent installations. And so with these, the trade-off between these two barriers in mind, Hydrotech developed a mobile DMA testing unit, or this cost-effective diagnostic field testing device, where essentially we have a metering chamber on wheels. And so we house inline flow metering technologies, as well as a pressure reducing valve in a truck. And so we have more spatial versatility that we can temporarily go to different areas of our systems, different temporarily configured district metered areas, collect data in a cost-effective manner. And so essentially, we're bypassing a valve in the system upstream and into the configured DMA. And so this was inspired by previous work from the City of Ottawa in the mid-2000s, where they partnered with the National Research Council on an experimental type project quite similar in nature, as you can see a picture of their setup on the right. So we can accurately and reliably measure low flows with this device affordably compared to permanent infrastructure. And we also have the bonus of directly testing the effectiveness of pressure reduction on inflow, which is a component, or leakage, a component of into the system. So we need to understand, before we deploy the unit, the head loss characteristics, so we don't drop pressures into the area too low. Initially, before deployment, we calculated a theoretical head loss curve using the conditions on the right. And so the losses are imposed through the connection, which are typically taps on both sides of a closed valve, or through hydrants on the upstream side of the system, downstream into the DMA, through fire hoses, typically about 25 feet long, to the mobile unit, and then the other connecting the downstream end to the DMA. And so if we compare with actual conditions using the same setup conditions, we can see here that there's a decent degree of less head loss in the system than was initially calculated. And so being quite a conservative approach, which is good. If we look at other cases, setup conditions, the difference in this blue plot being the tap connections were suspected to be smaller than the 2 inches originally calculated. As a result, we can see that our head loss has increased across the unit. And then lastly, if we increase, or when we did increase the size of our hoses connecting the system from 2.5 inch to 4 inches, our head loss has decreased. And so allowing for us to test in either larger DMAs or DMAs with greater leakage within them. So looking more broadly at the Ontario-wide testing program, there are 8 participating municipalities across testing in 20 DMA test sites. So far, we've tested in 7 of the 20 DMA sites, as noted here, with 13 more to go up until around this time next year. And so the subsidized testing program consists of us deploying the mobile unit across those 20 DMA sites to collect minimum night flow data, as well as test the effectiveness of pressure reduction on leakage reduction, which we'll report on results later in this presentation. And so as I mentioned, the testing is focused on residential DMAs over non-irrigation periods. so as to compare the sites that we've collected data for against each other in terms of performance, relative performance. And that's done through various different performance benchmarking metrics informed by the data. So looking at our testing setup, you can see the upstream, or the fire hose coming from the valve chamber through our unit and then back down into the system. We have our PRV on the upstream side of the mobile unit and our flow metering technology, inline flow metering devices. And then you can see at a close-up the connection, the taps across that, that closed valve. And then us out testing last November in Canadian winter conditions. This was the first snowfall or sub-temperatures that we experienced last year, and we were out enjoying the weather as we were testing. And still able to collect reliable results in this weather, although the personnel quite cold during the experience. So once we've collected the data, we've developed various different performance benchmarking metrics, essentially looking at that minimum night flow value normalized to various DMA characteristics, mainly characteristics of DMA size. And the objective of this is to derive a strong relationship among well-performing systems, and so as to identify any outliers or poor-performing systems that may warrant further attention and investment. And so that baseline of strong-performing DMAs is termed a minimum night flow frontier, which is a representation of those healthy systems. Very similar to the presentation last week that Alan Wyatt gave on using those utilities that were performing well as the basis for performance, objective performance assessment. And so this approach of using the actual data collected avoids any uncertainties associated with existing empirical formulations or estimations of how our systems should be performing. So as I mentioned, 20 of the DMA test sites have been completed. And the data that we're going to present in the following slides also includes 3 additional sites from previous DMA testing work that Hydrotech had completed a few years ago, and the data curated to the standards of this project. And so they're included in the benchmarking metrics. So the first, looking at the number, the minimum night flow plotted against the number of service connections. You can see here the minimum night flow frontier in the dashed line, representing that line of healthy system performance. And then 2 of our sites, clear outliers against other systems of healthier performance. Now looking at minimum night flow against the number of residential units, which is quite similar to the number of service connections, except for any connections that are to multi-unit residential properties are going to have higher number of residential units. And so this is a little bit of a stronger relationship we've found so far across that healthy system line, or that minimum night flow frontier. But again, we see that clearly we have 2 outliers of the 7 sites we've tested. Another one looking at the length of water main, which is typical for looking at the normalized performance of different DMAs. Not as strong as a relationship across that frontier, but again, we're still seeing these outliers in the point of analyzing this data. Interestingly, a presentation that we attended in the North American Water Loss Conference this past year by Alan Wyatt looked at an indicator blending the number of connections, or in this case, we've adapted to the number of residential units with water main length as another way to objectively assess the data. And again, as expected, we see these outliers appearing. So many different ways for us to assess. This is just looking at that blended rate, but just on minimum night flow plotted against it, which is the combined real loss indicator. And again, we have a very similar outcome. And then lastly, looking at the ratio of minimum night flow to average bill demand, being a characteristic of DMA size. As the DMA increases, we're going to have a larger demand in the system with these outliers. And so we'll look more closely at one of these outliers in the case study, and some intervention work that was done and verified through using the mobile unit. We look at pressure reduction. When we lower the pressure in the field in our testing, what outcome does that have on a lower flow, which includes leakage into the system? So we have our initial pressure, our in situ pressure, and then we can reduce that pressure using the PRV on board the unit, and then collect the data and see what the outcome is. And so this avoids the need of estimating or using leakage exponent, otherwise termed the N1 exponent, which has many different variables that impact this. And so when we're developing economic assessments of the impact of pressure reduction, we can directly see what impact it has. And so we can see our testing set up here with the PRV, which we employ. Now, looking at the results of pressure reduction, before I go into this slide, we started looking at one night of full pressure, collecting that overnight flow profile, and subsequently that minimum night flow value. And then on a consecutive night, dropping the pressure to a specified value, collecting that flow profile again, and looking at the delta, the difference, or the benefit in flow reduction. However, we did realize that there was some day-to-day, or rather night-to-night demand stochasticity. And so we were meeting with Professor Ivan Stoivanov from Imperial College London on other matters. We were talking about our work, and he had mentioned looking at a pressure cycling technique. And so as you can see here, the black plot, we have our high and low pressure, which is cycled on a 30-minute period. And then we have our corresponding flow values for those time periods, which are stitched together for the high pressure and low pressure flow plots. So thanks, Ivan, for your input. And so looking at the case study that I mentioned, here is an overview of the DMA, the black outline, our mobile testing unit connection at the top right into the system, and then a critical monitoring point to ensure we're not dropping pressures in the system to below standards. So this was the first DMA site in the Ontario-wide testing program. And interestingly, initially, before deployment, this specific utility wanted to implement permanent pressure management. However, due to many known issues in the area, greater than normal historic water main break frequencies existed in the area, and they were looking at reducing the pressure to help these things. However, as it related to direct benefit of leakage reduction from a lower pressure, there was no data or evidence to suggest or warrant this implementation. They had implemented temporary flow metering, which we had touched upon previously in this presentation. And due to those low velocity limitations, there was no reliable data collected with that exercise. And so this presented itself the perfect opportunity to deploy our mobile testing unit. So initial results, the setup on the right here, and then the flow profiles. So this was the first site, and so that pressure cycling technique was not implemented in the first go around. And so the orange plot is the full pressure that was in the system, and then on a subsequent night, reducing that pressure. And so there was modest benefit to pressure reduction in the DMA. However, when we looked at the results on the benchmarking metrics that were developed or being developed in this project, there was quite a healthy departure from the minimum night flow collected in this system compared to that frontier value. To be exact, around 5 liters a second was estimated as recoverable leakage. So this is equivalent to just under $500,000 per year. Note that this is a utility that does pay quite a bit for their water, as they do not source their own water, but rather purchase from a upstream municipality. And as I mentioned, pressure reduction of around 10 psi offered a modest reduction in leakage. But the recommendations post-testing was to conduct a leak survey and look further to see if any leaks can be repaired, to which the municipality did just that, found a leak, and then subsequently repaired it. And so we were sent out again to verify the leakage reduction or the recovered leakage as a result of the repair. You can see here the orange plot is from initial testing, and then in green was the post-repair testing. And so the flow profile being quite a bit lower of around 4.5 liters per second as it relates to that minimum night flow value. When we did pressure reduction testing again, we can see the same decrease in pressure across the system, and the flow profiles of both the high and low pressure intertwined and didn't show any benefit or material benefit of as it related to direct leakage reduction or inflow reduction to the system. So when we look at the benchmarking metrics, two of them being here, the number of residential units normalized to, as well as the ratio to the average bill demand. We can see initially the DMA plotted as labeled, and then after the leak was repaired, we come down quite a bit into a region of its healthier peers and closer to that frontier. And so we can quantify that. And that was roughly 140 million liters per year, which is quite substantial. At the 2019 rates, around $430,000 a year was recovered or saved, and close to 470,000 when the 2020 rates were imposed, and then the resulting energy savings as well. And so looking at a economic evaluation from before initial testing, before the leak was repaired, to the retest, we can see that just looking at the value of water alone, the blue column is the overall leakage reduction potential. And so, and the orange being that of pressure management or pressure reduction. And as a resulted from the repair, those values considerably went down. And so key recommendations after the retest, well, we know this area has known issues. And at the time, pressure management is not economical as it relates to the direct benefit of leakage reduction, which is informed by the testing results. But monitoring is clearly valuable, at the very least going forward through periodic temporary measures such as deploying the mobile unit or through permanent installations. And then also considering other longer term indirect benefits. So the key takeaways of this presentation was first looking at the assessment of uncertainty in our initial efforts for water loss management, specifically as it related to the top-down water balance and quantifying the range of possible outcomes that may come from those assessments. And then looking at cost-effective bottom-up practices, specifically the mobile DMA testing unit, which is a cost-effective diagnostic tool to monitor system performance and inform further water loss investment decision-making through the collection of minimum night flow as an indicator of leakage, as well as testing the effectiveness of actual pressure reduction on leakage reduction in the system. And so using the various evidence-based benchmarking metrics that are being developed, we can objectively assess DMA performance. Additional information on the project can be found at the following webpage, where project-specific documents are contained, recent publications, and conference presentations. Upcoming events, we will be presenting next year around this time at the IWA's World Water Congress in Copenhagen, Denmark, which we're looking forward to. And then a publicly available report through the IESO on this project detailing findings and recommendations will be available sometime next summer. Project acknowledgements, again, as I mentioned, IESO is the primary funding agency supporting this work, along with other various entities in the National Research Council of Canada, industry partners, the Ontario Waterworks Association, University of Toronto through Professor Brian Carney, of course, technical reviewing help from Dowie Rogers, instrumental throughout different stages of this project, and then the various participating municipalities as seen here. And as I see, many of you are joined today on the webinar, so thank you for listening in. With that, thank you. Thank you everyone for listening, and we'll open up to questions. hopefully I'm not too off on time.
That's perfect. Thank you, Bradley. We don't have any questions right now. Just wait for some minutes now.
Sure.
Thank you for your presentation. It was really great.
Awesome.
Actually,
thank you.
a great number of participants watching your presentation. That's really
Cool.
great. Oh,
Milene?
Hi.
It's Alan.
Hi.
I sent a couple of questions directly to Bradley. I guess I should have sent them to everyone. But
Yeah,
you can read them. You can read them.
Yeah, but Bradley, I can't see the private questions.
Yeah, so I've got these questions up. We'll start from the first question from Alan. I see it chimed in.
Let me just interrupt you. Everybody who wants to send any questions, please send in the chat box, but to everybody, please, so I can help Bradley with this.
Just reading through your message, Alan. Give me 1 second.
You can read it aloud so everybody can understand the question.
Sure, to see if I can comprehend it first. Okay, I've seen many presentations, data sets where they just represent energy efficiency using kilowatt hours per cubic meter, presumably because they don't understand or they do not have dynamic head. I know they are mangling the theory, but as a practical approximate measure, is this formulation really misled, but adequate for an initial screening tool? Alan, do you want to follow up on? I think you've got a little more here.
Well, I just, I don't know how bad an indicator that is, and from your experience, how bad is it? Can it get you in the ballpark?
Yeah, I'll let Fabian Papa chime in here for you.
Hi, Alan. Fabian here. I'm responding to the part of the question about the kilowatt hours per meter cubed and that is typically called as specific energy. And I agree that can be a misleading indicator. And normalizing it against head, the dynamic head in particular, is we've shown to be very valuable. We've tested a number of pumps and done the normalization on that, and the curves are very crisp and within a narrow range when you do normalize against both flow and head. And remember, a pump is delivering, or even water power is the combination of both flow and pressure. And so not normalizing against them both, you will end up with a lot of noise in the data. So what I'll do, I'll try to follow this up with an email to you, which has a report that has those pump testing results. I think I may have shown them to you at one point in time several years ago, but a refresher might be in order.
Well, that would be great. I just think in a lot of countries they don't know, or they don't have the data on even the static head, so.
Right, and that has been the challenge. Actually, I think it was in Cincinnati when we presented alongside with the Mexican water utility, comparing what we were doing in Ontario versus Mexico. Here we had specific data for tests, and in Mexico they were collecting data from utilities, many of which were not providing clear precise answers on the head, and their results were all over the place, some of which were outside of the realm of technical feasibility. So you're on the right track.
And then the second part of your question, Alan, looking at the combined real loss indicator in our work. Yeah, absolutely looking at, or would be interested in looking at this further with you. In terms of looking at different system attributes, again, we don't have a lot of data so far that's been collected. And we've a preliminary look at different relationships haven't been quite strong, but as we collect more data, absolutely, this is of interest.
Yeah, what I was trying to get at is you could see the sort of origin of the problem, diagnose what's going on, why those ones are way up in the sky, so.
Right.
But it would need testing and work, so.
Yes. David Taylor, or
we do have another question here. Can you explain the graph on slide 43 again, please? Are big bars good or bad?
Yes, this is from David Taylor. So I've got the slide up here now. So initially, when there was lots of recoverable leakage estimated in the system, big bars being bad in that there's a lot of recovered leakage to be had, and so essentially the blue plot, the blue bar plot here is how much warranted investment or how much investment is warranted to reduce that leakage. And so this is a function again of the cost of water in this specific area, which is quite high. And so therefore, almost anything that has been done in this system will help to reduce that. I hope that answers. And then as a result of the repaired leak, that value decreased significantly.
Great. And then the orange ones?
So that's looking at the value of pressure management as it relates directly to leakage reduction. And so the first time around, when the leak existed in the system, when we reduced the pressure, we did see a modest benefit of the inflow or leakage reduction. But when we tested after the leak was repaired, there wasn't much value seen from the data.
So this is saying that even without fixing the leak, if they had done pressure management, they could have saved 170,000 a year or something like that.
That's correct. Yeah.
Great.
Yeah, I think the other way to look at it is this is how much you can afford to invest. And that would be the present value of, I can't remember what metric we used there, but this would provide you a return on your investment. It wasn't a one-for-one sort of thing. It was better than that.
Excellent. Thank you.
Good question, David.
Any more questions?
Yeah, there might have been. Let me just pull up the chat again.
We've got a great job, Bradley. I have to run, but really enjoyed their presentation. Love the emphasis on uncertainty, which is so often reduced to deterministic absurdity. So great job, Bradley.
Excellent. Thank you. Thank you, everyone.
We've got thank you for hosting. Next time, I advise us to send our questions to all. That's perfect. Did you get any more questions on private?
I haven't received any further questions. No, not that I can see. Oh, yes, there was one from Romalyn Mousy. Sorry if I pronounced your name wrong. Hi, Bradley. Can you show us a schematic diagram of the mobile unit and the underground pipe to where it will be connected? So I believe we showed that on a previous slide. Let me get back to there. Sorry, one moment. I think this is the slide that you're referring to. And so we're connecting the fire hoses on both sides of that closed valve through these tap installations, both on the upstream and the downstream side of the system. And so that's how we're able to bypass the flow across the valve outside of the system into the unit, so we can collect our data or reduce the pressure if that's the intended purpose, and then the flow is routed back into the system. So I hope that got another message.
We've got another one. How did you handle correlations in your MCS? It's from David Taylor.
For the Monte Carlo simulations, and so the input probability distributions or correlations between the data, if that's what you're referring to, David, and if there's any, whether that's the system input or otherwise, if the correlations between them, we didn't consider that. We just assumed that every input into the model was independent in nature and was just using that as a method to also calculate the uncertainty. But no correlations. No correlations were assumed in the approach.
Okay, thanks.
Question.
Any more questions?
Nope, just a few. For a copy of the slides, you can send an email. I'll get up our emails. And we'll be happy to send you the slide deck today. Yeah, and as well, the presentation will, of course, be on the YouTube channel of the IWA Water Loss Specialist Group. So you can take a screenshot of that if you'd like.
So I think if we don't have any more questions, we can call it for now. Thank you
Perfect.
very much, Bradley. It was a really great presentation. And thank you very much. If you want to say bye to everybody.
Oh yeah, thanks to everyone for listening and for the comments and feedback after. Appreciate it.
Thank
Take
you
care.
very much. Bye.
Thank you.
Thank you. Thank you.
Bye.